So let's look at these graphs of functions. The first one we remark for this first graph. Okay, we remark that that the function is not defined at x0. So the domain here is r minus 0. Okay, so there is a hole in the graph. Okay, so we have a hole here. Okay, let's say a hole, small hole. Here we have also a hole, but f is still defined at x equals 0, and the domain so is defined f defined, but is defined everywhere, but there is a hole. Okay, still there is a hole. Here also, here it is defined at 0. It everywhere 0 and no x is different, is defined everywhere, but the graph there is like a jump to infinity of. Okay, so we have jump to infinity. Here there is a hole. Okay, okay, and plus jump. Okay, and here if you look at it also there is a jump. It is defined and there is a jump. Okay, so this kind of behavior is called discontinuity. Okay, so we are looking for characterization of function, so more properties. Last time we learned limits locally, what is happening. We developed the concept of limit, but now using the limit we want to look more finite properties. Okay, this is the continuity. So a continuity, like we understand it, is something without interruption. A graph, continuous graph, we will look at it as a graph without interruption. So we will define here the we will give the definition of a continuous function as the function. So here is the definition. So we will say that f is continuous at x0 if and only if. So we would like to avoid this jump. We will avoid it if f is defined at x0, for example this hole. So we need f, so f at x0 defined, and we want also to be sure that the limit when we approach, as x approaches x0, is equal f at this x0. So this is the definition we give for continuity. Okay, and with this definition we can have if we have continuous function, we can then have more yes, we can have more functions. We can build many functions by this theorem, by operations. Also we can prove using just the definition that if we have f, g continuous functions that are continuous at x0 and c a constant, okay, c a constant, then we can show that f plus or minus g is continuous, or not just. Let's continue also. The other functions are also, we will have what else, fg, the product fg, also continuous. Okay, the product CF, the constant and CF. What else? F times G and F over G. Okay, with if for this condition with G at a different from 0. Okay, are continuous. So are continuous at A. So knowing few functions that are continuous, we built new other functions. Okay, for example, we know that examples that you know already, you have polynomial functions. Polynomials are continuous function. So to avoid writing continuous, I will put this symbol C0. Okay, C0s. Okay, fractions, rational fractions. Okay, so rational fractions are C0 on their domain. Sorry, let's correct this. Yeah. Okay, are C0 on their domain. What else? The other example is the trigonometric functions. So the function that assigns sine x, x sine cosine x are C0 on the interval R. So here we spoke at the beginning, the definition we gave it at a point x0. So here I need to correct here, it's x0, it's not an A. Okay, so it's not, it's an easy. Okay, at x0. Okay, but here I started speaking about an interval. Yes, we can generalize the definition to an interval. Here it is. We say that f is continuous. F is C0 on an interval AB. Okay. So let's understand for on R for each point. Okay, on interval, open interval. Let's say. Okay. EB, or I will give it anyway. You will see why I'm hesitating. So f is C0 on EB if and only if f is C0 at each x belonging to the interior of the interval, each x0 belonging at the interval. So we apply the definition plus, and so we need to check this, and f is C0 to the left of A, and f is C0 to the right. No, to the right. So to the left of B and to the right of A. Okay, and we understand here the definition of. We assume that we can extend this definition. So this is one-sided continuity. So f continuous at x0 to the left if and only if you can have limit. So the fx as x approaches x0 to the left equal fx0. Okay, and similarly f continues at x0 to the right. Okay, if and only if you have the limit for x0 plus. Okay, etc. Similarly. Okay, so we know we have many functions, family functions. Okay, so there is now an important result here. using continuity, two important applications of continuity. The first one, it allows us to compute more limits, more complicated limits. Okay, so let's see this one, computing limits, computing new limits. How? You will see. So here is the theorem. The theorem says if we have a limit of fx exists, okay, if you have the limit of g of x, if we have limit of g of x equal at L as x approaches x0 and f is continuous, f c0 at L, okay, is continuous at L, then what happens? The limit of f of g of x as x approaches x0 is fl. You can compute it like that, f of the limit of g of x, like you put the inside the limit. Okay, and this is important because it will increase for us more, it gives us more possibilities of computing limits. Okay, for example, let's say limit of sine, it's okay, so limit, for example, limit of sine, let's say x3 plus x2 as x approaches, yes, or let's use something more complex than this one. Let's take an example more complex than this one. Yes, for example, I would like to compute the following limit, okay, approaching x0 of, I will use sine x, this particular limit, and I will use 20 like that. Okay, so I see my function here is a composite function. I can identify using the notation of the theorem g of x as sine x over x, and I know that limit of g of x as x approaches 0 is 1. The limit exists. It's a particular limit that we proved, that was established using the comparison theorem, okay, for limits. And the other function is power function. Fx is, I will call it x power 20, okay, and I know it's polynomial, it's continuous, so a limit of fx here as x approaches, f is continuous at L, so here L, this is my L at 1, so you can even change the value notations if you want, but it's you can follow like that, it's okay. So it will be 1 power 20, which is 1. Okay, so here I can say, because I know the properties, f is continuous and this limit exists, and f c0, here f is c0 everywhere, so yes, it's stronger property. So here I can say it's the same as putting inside the limit, computing what we know, and then make the calculation. Okay, so it will be 120, which is 1. So it's a way, yes, it allows us to make more calculation now, like that. Okay, the second application of continuity, an important one also, is the intermediate value theorem. You will see it, what it says. The intermediate value theorem. Intermediate value theorem. So as abbreviation we will use EVT. Okay, here it says the following: we need a function that is C0 on a closed interval. So it is important, closed. Okay, what else? Okay, and key a number key between, okay, between FE and FB. Then, so for any key is any number between FE and FB. Okay, then there exists. Okay, there exists. So this means there exists this symbol. Okay, there exists a number C inside the interval such that also we will use this abbreviation such that FC equal K. So let's try to understand what the theorem says. So graphically, let's do some small graphing here. Okay, X, Y. So let's have A, B, and we have a curve. Here is FA. It does something like that. FB. So here is my FA. Here is my FB. Okay. Then the theorem says any key I choose from here somewhere between FE and FB, any key you choose, then we are able to find a C somewhere between E and B so that FC, so FC will be exactly K. Okay, that means the equation, okay, here FC equal K, that means the line Y equal K is a line, an horizontal line. If you choose Y equal F, if you write Y of X describes the curve of describes the formula F, then the intersection is not empty. Okay, so the intersection of the line and is not empty. That is, has a solution. Okay, and here for example you see we have three possibilities in the graphing. This graphing shows that we have not necessarily only one solution. The theorem doesn't say only one, it says at least there exists only. That means it can be at least one. For sure there is one at least point. It can be more, like we are seeing this. So this is the intermediate theorem. It's important one, and as an application we use it for solving equations. Okay, let's see an application of the theorem. Okay, here it is. So we are asked to show that we have a solution in this interval. Okay, show that the equation has a solution. 4x3 minus 6x2 plus 3x minus 2 equals 0 has a solution between 1 and 2. Here they gave us an idea between 1 and 2. Okay, so I will try to let's try to apply the theorem here. So we want to solve an equation here, a quantity. You see, equation, we know we have control on solving equation of degree 1, degree 2, but more than that, yes, it's hard. It's complicated. Degree 3 already it is complicated. So here the theorem, if I try to equal K, if K I use it here 0, let's just try to work like that. So set k equal 0, fx, I will use this quantity. I will denote it fx, okay? And so we want to solve the equation, okay? Okay, fx equals 0, okay? So solve the equation fx equals 0. So let's check the assumption of the theorem. Yes, f is polynomial, so it is continuous, okay? So I need the continuity. So f continuous, f c0 everywhere. So for no problem for this. We need the value f1. f1 is 4 minus 6 plus 3 minus 2, which is equal to minus 1, which is yes. And f2 is 4 times 8 minus 6 times 4 plus 3 times 2 minus 2 will be equal 12. And I see that k which is 0 is between f1 and f2. So I can so by the intermediate value theorem, there exists for sure a C between 1 and 2 such that fx equals 0. And this is what we wanted to do, okay? To show that we have a solution. Okay, something else we can do if we repeat, if we can use the intermediate value theorem to locate. Okay, so this is, let's put it as a remark. IVT is used to locate more precisely the root, okay, the root by reducing, okay, by reducing the interval. So if, for example, in this situation, we are sure along the interval 1, 2, here is 2, here is 1, we are sure that we have a root. So the idea is why to test, not choose other values smaller. Here, reduce the interval until we approach more and more the solution. Okay, why not then approach it like that? Okay, for example, if we compute here f, look, 1.2, here is 1.2, okay, we found the value minus 0.128, which is less than 0, and f13 1, yes, and which is less than f13, less than okay, less than 1f, which is 0.548 f13. You see, that means I have a root k. This is my k. I found it between the two images f12 and f13. That means the root, there is a root c. C is between 1, 2 and 1, 3. You see, from the whole interval 1 to 2, we are sure now that we have a root here. Maybe there was more here, there are others, but at least we are locating more precisely with 1/10 precision. Okay, look, another test here, another comparison here. F122 is minus 0.00708, which is negative and less than. Look at 0.25, which is not 0.25, it's 0.5 here. 0.05, it's f123. Okay, so there is a c in a more smaller interval. 1, 2, 2, let's say here 1, 2, 2, 2, and 1, 2, 3. You see, 1, 2, 3. So C here, we are sure we have a C here, and 1, 2, 3. So this is a property of continuity. Mainly you have, so the definition to know. Okay. So we have mainly what we saw today, the definition of a continuity, how to form a new continuous function by operations of on functions, adding, multiplying by constant, or product of between, or dividing. We know family of function that are continuous. Then the left continuity, right continuity, which is useful property also. Computing limits. So using, yes, one at least of the function is continuous, and the other, the inside, has a limit. So we can compute like that new limits. Okay. And the last more important result is the intermediate value theorem, used to solve equations.